Now in this lecture, we take some more examples on Lagrange's mean value theorem. Let us first take what is the statement of Lagrange's mean value theorem. Let f of x be function of x defined in the interval ab such that first f of x is continuous in the closed interval ab. Second, f of x is differentiable in the open interval ab. And third, f of b is equal to f of a. Then there exists c in the open interval ab such that f dash of c is equal to f of b minus f of a divided by b minus a. Now, this statement can be also written like this. Let f of x be a function of x defined in the interval a plus a plus h. H is very small number such that first fx is continuous in the closed interval a plus h. Second, f of x is differentiable in the open interval a plus h. Then there is at least one number theta which is lying between 0 to 1 such that f of a plus h equal to f of a plus h times of f dash of a plus theta h. This is another formula which can be obtained by using the Lagrange's mean value theorem. So the one formula is this. For generally we are using this formula for Lagrange's mean value theorem, but sometime for proving some fundamental result we can also use this formula. So now let us take one example which can be solved by using this formula. Prove that log of 1 plus x is equal to x upon 1 plus theta x, where theta lies between 0 to 1, and hence deduce that x upon 1 plus x is less than log 1 plus x, which is less than x, where x is always greater than a. Yeah, we can say that this x is always greater than 1. Let us try to solve. Let f of x is equal to, here it is clear that f of x is nothing but log 1 plus x. So let us take f of x equal to log 1 plus x. If we differentiate with respect to x, derivative of f dash of f of x means f dash of x is nothing but 1 upon 1 plus x, because derivative of log x is equal to 1 upon x. Therefore, derivative of log 1 plus x is 1 upon 1 plus x. By second form of Lagrange's mean value theorem, we have f of a plus h equal to f of a plus h f dash of a plus theta h, where theta lying between 0 to 1. Putting a is equal to 0 and h is equal to x in the above equation, then it will convert to a is equal to 0, a is 0, and h is equal to x. So the first term becomes f of x. F of a is replaced by 0, so f of 0. H is replaced by x. F dash, a is 0, theta is theta, and h is equal to x. So f of x equal to f of 0 plus x times of f dash of theta x. But we know that what is f of x? F of x is nothing but log 1 plus x. F of 0 is, substitute x equal to 0. So log 1 plus 0 plus x times of f dash of theta x. So f dash of x is 1 upon 1 plus x Therefore, f dash of theta x is 1 upon x plus theta x. Let us simplify it. Log 1 plus x is equal to log 1 is nothing but 0 plus x upon 1 plus theta x. I think this is our first result. This is our first result. Now from this result, we have to deduce the second part. X upon 1 plus x is less than log 1 plus x, which is less than x. Since we have 0 is less than theta, theta is less than 1, means theta lies between 0 to 1, which implies 0 is less than theta into x is less than x because for any positive value of x. Here we are considering that x is always positive number. Now, so we have multiplied this whole equation by x. Now adding 1 to the whole inequality. So 0 plus 1 is 1. 1 plus theta x, which is less than 1 plus x. Let us take its inverse. So 1 upon 1 is the less than sign will be converted to greater than sign. So 1 upon 1, which is equal to 1, greater than 1 upon 1 plus theta x, which is greater than 1 upon 1 plus x, which implies x is greater than, we are multiplying, we have to multiply x by whole to whole inequality. So 1 into x is x, 1 into x is x, 1 into x is also x. Now, we have to write this in the less than sign. We have to first write x upon 1 plus x, which is less than x upon 1 plus theta x, which is less than x. Now here log 1 plus x is equal to x upon 1 plus theta x. So we can replace x upon 1 plus theta x is equal to log 1 plus x. Therefore, x upon 1 plus x is less than log 1 plus log x, which is less than x. And this is our second part of this question. Thank you.